Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillah, and a very good day. So we meet again. This is, I think, probably the last video for SKEE or SEE 2423 for session 2020-2021, semester 1. Okay, and also this is the last pre-recorded video for this subtopic, which is the three-phase induction motor. Okay, so in previous lesson, what we have discussed is actually we have already know the model of the uh, three-phase induction motor. Okay, and then we also have discussed about how to obtain the parameters value, which is the stator resistance, which is R1, X1, the rotor parameters, and so on. Okay, and in this video, what we will discuss is about the performance of the induction motor, okay, by using that model. So as can be seen here, this is the what we call the single phase equivalent circuit of the induction motor. So we have this one, your stator, and then this is your copper and also magnetization effect, and then this is the rotor side. Okay, and for the input power, so even though this is a single phase, but usually we will conduct our calculation in three phase. So just multiply with 3. So V1 and I1 cos theta. So this cos theta is the power factors. And you should note that V1 and I1 should be in phase values. Okay. And then at the stator side, we have losses due to the internal resistance of the stator. So this can be calculated by using this equation. Okay, and then we have also copper losses, RC. So just RC here. So since RC is actually parallel with the voltage input, so you can use this equation to calculate the losses due to the core losses. These core losses is actually we have what we call hysteresis due to the hysteresis effect. Okay, and the second one is due to the eddy current effect. Okay, and then this is at the stator side, and then move on the rotor side. We have this is the power that has been transferred to the rotor, so you can calculate by using this equation. Sometimes this one is also called a power air gap. Okay, so 3 multiply I rotor square multiply with R2 over the slip. Okay, and then the last one is actually the rotor copper losses, which is you can calculate by using 3 multiply with I square, I2 square multiply with R2. So as you can see, this one is actually if I redraw back, okay, this one is actually equals to R2, and this one is R2 as 1 minus S. Okay, is it? I think this one is correct. Yes. Okay, so this is your I2 here. So this component here, R2, will actually represent the rotor losses, and this one will represent the P out. Okay. So the gross output power, so this one is actually P out. This one is your power that actually transferred to the rotor minus the losses at the rotor side. So we have that your P out, which is equal to P air gap multiplied with 1 minus S. Okay, and the power at the drive shaft, so you need to consider the friction losses. So the power at the drive shaft, you need P out. Okay, this one P out minus the friction losses. So this is the actually net power at the drive shaft. Okay, and then we have also what you call the developed torque. So the developed torque you can calculate by using P out over the speed, and this speed must be in radian per second. Okay, so how to change from RPM into radian per second is just you need to multiply the motor speed in RPM multiply with 2 pi over okay, over the frequency. Sorry, over 60 this one. Okay, I think this one is actually elaboration of the torque. Okay, from here, actually this one come from here, which is you can elaborate more. Okay, but I think I stop here. It's good just to know until this part. Okay, and then we go for example. So a single phase equivalent circuit of a 6-pole 6-pole induction motor that operate from a 220 volt line voltage at 60 Hz is given below. So it has been given the stator parameters and also your rotor parameters. So calculate the stator current, the input power factors, the output power, torque, and efficiency at slip is equal to 2.5%. So S meaning that S is equal to 0.025. The fixed winding and friction losses, okay, is 350 watt. Okay, so and then neglect the core losses and calculate the starting current. So the solution is given here. So we have V1, I1, and R1, X1. We have XM given 20 ohms, X2 is 0.2, and R2 is 0.1 ohm. So first, what you need to do is to get what is the power input. So to get the power input, one you need to know is actually to know I1. Okay, so to get the I1, what you can do is actually to get the total impedance. Okay, so the total impedance, so in that you need to know this one. Okay, so calculate what is your Z input. So this one R1, X1, R2, and X2. This one is XM. Okay, so this one R1 and X1 plus JX1 XM parallel with this one. So this one should be R2 over S. Okay, and the slip is right now S is 0.025. So when you calculate, so you will have that your Z input is 4.2 with an angle of 20 degrees. And then by using this formula, so I1 is equal to V1 over Z input. So you will have the current is 30 ampere with negative 20 degrees. Okay, and since V1 is as our reference, so meaning that the angle theta is actually 0. So your power factors, okay, so theta V minus theta I is 0 minus 20 degrees. So you will have cos, this one is cos, okay, cos 20 degrees. So you will have, so V1, and V1 is your V phase, okay, so you need to convert 220 volt V line over square root 3. Then you will have your P input is equal to 10.75 kilowatt. Okay, and then we have losses at the stator side. So just use the stator losses equation. So you will have the value is around 540 watt. So the power transferred to the rotor, which is the P air gap, which is you need to the input power minus the losses. So this is the power that has been transferred to the rotor. Okay, so the gross power, meaning that this is the power mechanical. You can use P gap 1 minus S. Then you will obtain the value is 9.9 kilowatt. Okay, so this is the power of the mechanical. Then and at the shaft, meaning that the power at the shaft transferred through the drive shaft. So you need to consider the friction losses, which is 350 watt. This one has been given. So the final power output at the shaft is around 9.6 kilowatt. Okay, and then the efficiency you can calculate by using output power over versus the input power. You will obtain around 89.3. Okay, and then the torque, you can use this equation. Always use this equation where the power output is 9611 over the speed of the motor, which is this one you need to use in the radian per second. So you will obtain that this one is around 78.4 Newton meter. So actually to get the speed, okay, as it has been given, so 0.025. So you can always use this formula first. So ns minus n motor over ns. So this one is 0.025, where ns is actually 120 multiplied with 60 hertz over the number of pole, which is 6. Okay, so this one is around 120 multiplied with 60 over 6, so 1200. So your motor is, okay, multiply with 0.025. So your motor speed is actually 1178, but this is in RPM. So 1178 RPM is equals to, you need to multiply with 2 pi over 60. So this one is around 122 radian per second. So this one is actually 122. So 9611 over 122, we should get around 78.7 Newton meter. Okay. So I think this example conclude our presentation, conclude our lesson for this performance characteristic of the three-phase AC motor. Okay, sorry. So the last question. So the last question is actually to get what is the starting current. Okay, so to get the starting current, what you can do is actually you can always set, this is the Z impedance. So I1 is V1 over Z in, and as you can see, Z in here is actually depends on the S slip. So when you set S is equal to 1, so you will have these values. Okay, 100, which is your current, starting current is around 167 ampere. And this is actually 5 times from the full load current. The full load current that we calculated is around 30 ampere. Okay, so this is the full load current, which is a steady state current. So this is 167 ampere, meaning that during the startup, it has 5 times from the, this is your 30 ampere, so this is your 167. This is the starting current, so which is a very high, but this is actually common for all induction motor. Okay, so care should be taken when starting the induction motor, and that's why for AC motor, it is the bill is quite high, because when the motor is start up and start down, always is actually in starting and then shut down and then starting again and so on. So your bills will be very, very high due to the starting current. Okay, this can be the good example is your air conditioner, where actually for air conditioner we are using a single phase induction motor. Okay, so the compressor, which is the outdoor unit, as you can see, when it reach its temperature, desired temperature, the compressor or the motor will stop running. Okay, and when the temperature is getting hotter, then your motor will start rotating again to compress the air. So that's why this start up will actually make your bills become higher. So that's why to reduce this start up, we are using what we call the inverter technology, where we make sure that the motor is always running, is always on. Okay. So this one, another example, I think if you have time, so we can actually try to solve this one. Okay, so I think that's all for this lesson. So inshallah we meet again next time. Thank you very much.